If you have seen the introductory video to this channel, you might know that I'm a PhD in astronomy, and I have also mentioned in that video that I have given many public talks and lectures. So what is astronomy? Astronomy is the study of celestial objects. What is particle physics? It's the physics of the minutest of particles that make up the universe. What is evolutionary biology? It is a study of the theory of evolution. And what is common to all of these sciences? Well, they are what we call basic sciences. So these are sciences where the study of these sciences is done in order to just understand more, in order to satisfy our curiosity of what is out there, and in order to acquire more knowledge, explore new techniques. But seldom will you find a particle physicist or an astronomer telling you that they are doing this in order to solve the global warming problem, or to solve world hunger, or to cure people of diseases. That is the job of applied sciences. So applied science is about using science specifically to solve a well-established problem, like the examples that I just gave. Now that is one thing. The second thing is the cost of doing basic sciences. For example, the 30-meter telescope, which is going to be a very important telescope that should hopefully come up in half a decade, is going to cost us $1 billion. That's a B for billion. The square kilometer array, which is another fantastic facility that should come up in a similar time scale, costs about $1.8 billion. One of the most well-known particle physics experiments, the Large Hadron Collider, costs anywhere between $7 to $9 billion. One of the most expensive experiments that has been funded in science. Now, when I'm giving these public lectures, people often ask, what is the use? There is no use of studying the exotic particles. There is no use of studying astronomy. So far away are these objects. And you're spending so much money on them. And there is no use. You're not going to solve the global climate problem. You're not going to solve the world hunger problem with this. So why do you do this? This is a question that is often asked. So this video is about trying to answer this question. Why should you study basic sciences, or why should basic research get funding? My first answer will start with the money aspect. Yes, $1 billion is a lot, $1.8 billion is a lot, $8 billion is a lot. But don't look at just the number. Also pay attention to what percentage of a country's expenditure is on basic sciences. So if you take my country, India, for example, the percentage is somewhere between 2 and 3, depending on which data and which year I look at. Even a very advanced nation is of similar percentage. It's not substantial. Money spent on defense or military, for example, is much more than 2-3% of what we call the GDP. And on top of that, you have to understand that when we say $1 billion for a telescope like the 30-meter telescope, we are talking about 10 collaborating countries spending this money across, say, 5 to 10 years. Then the numbers actually start looking very small. So let me assure you that compared to what money we are spending on many other things, the money spent on basic research is not substantial. Now the second important thing, what seems like a useless activity or a pursuit can become very critical tomorrow, day after tomorrow, several years from now. And I want to spend the rest of the video giving you some examples of this. Let's start with your favorite survival tool, which is Wi-Fi. So every smart device, whether it's a smartphone or a smart TV or a laptop, it has a Wi-Fi chip on it. And gone are the days when we used to take a wire and insert it in our computer. mostly our internet access is now wireless. That Wi-Fi technology, by the way, came up because there was a radio astronomer who was trying to solve some challenge in wireless communication. The scientists responsible for Wi-Fi were not imagining a future where Wi-Fi would be important. They were trying to solve a curious problem of wireless transmission, efficient wireless transmission, and Wi-Fi was a result of that. Let's talk about quantum mechanics. Very esoteric branch of physics. Very strange things happening there, and when people hear about it, a lot of people think this is all nice and fun, but not really relevant for us. Well, think again. It's because of quantum mechanics that we understand how semiconductors work, and it's because of semiconductors that all the electronic technology that you see today has been possible. It's because of quantum mechanics that we can maintain timing with extreme accuracy, what are called atomic clocks. It's because of quantum mechanics that we have access to lasers, and we all know how useful lasers are. Quantum mechanics is what allowed us to discover a process known as magnetic resonance, and those two words, magnetic resonance, are the two words of MRI, that is two of the three words in MRI, magnetic resonance imaging, and MRI scans are critical for medical diagnosis today. So it is very ironic when people say quantum mechanics has no real life application. Look around you, everything is quantum mechanics based. Now let's take another example. You have electronic deliveries now. Most of our shopping happens online. You have a fleet of trucks, bikes, and other delivery vehicles which are moving around. They hardly call you except when they are outside your house saying, hey, we are here to give you what you ordered. So how do they find your address that easily? Well, all of this is possible because of GPS. And GPS involves a series of satellites swarming around the Earth, coordinating with each other and helping in the location of your devices. Now, a very important thing. There is a clock on Earth and there is a clock in the satellite going around the Earth. There has to be perfect timing between these two. To maintain high precision clocks, you need knowledge of quantum mechanics. They are called atomic clocks, right? But there is another important process. Einstein's theory of relativity, general theory to be more precise, says that the rate at which time flows is different for the satellite because it is in a weaker part of the Earth's gravitational field, and different for clocks on Earth because they are in a stronger part of the Earth's gravitational field. Without this correction between the rate of time in a satellite and on Earth, GPS would not be possible. So Einstein's theory has immediate practical applications in our daily life. And Einstein's theory, by the way, is powered by what is known as Riemannian geometry. And back then when Riemann was coming up with the study of his geometry, nobody would have imagined it would become so important. Prime numbers. Mathematicians studied prime numbers out of curiosity. Today, prime numbers are very important for data encryption and data security. Yes. Check that out. Prime numbers are very, very important. Now, let's look at one final example of a technology that we all use. So it started out something like this. There were a group of particle physicists running experiments, and there was a need to share data across multiple computers. And it was proving to be a very frustrating and inefficient process. And Sir Tim Berners-Lee, who was a computer scientist working with these laboratories, came up with a new method of distributing data and sharing data between computers. And today it is known as the World Wide Web, which is what you use on a daily basis every time you open your browser and visit a website. Nobody created the World Wide Web for creating what we see today. They were trying to solve a problem, not related to the future of the world. So this is how knowledge that proves to be not so useful today can prove to be immensely useful tomorrow. And it is for this reason that it is important for every country and the world as a whole to ensure that pure or basic research is always funded. Thank you.